This year's a review. There are blank grams and 13.3 moles of lithium nitrate. Correct answer here is 917. 56% of you got that right. So let's just do a quick review calculation here on this one. We are starting on this particular one with a 13.3 moles of lithium nitrate. And if we're trying to get over to grams of lithium nitrate, what do we need in order to make this conversion? The molar mass. Good, we need the molar mass. So we'll slide this over here a bit. And how do we find the molar mass? Add what together? The atomic masses. So if you don't have your periodic table out, we're going to be using it a whole lot today. Let's get it out. If anybody needs a copy of the periodic table, raise your hand. I have some more here. You never have too many. Yep. Anybody else? All right. Okay, so if we want to calculate the molar mass of lithium nitrate, we need 1 lithium, we need 1 nitrogen, we need 3 oxygens. You sum them together. In the case of lithium nitrate, you should have that work there already. What is that molar mass? How much? 68.95. Okay, so if it's 68.95, where does the 68.95 go? On the top. Okay, because if there's 68.95 grams of lithium nitrate, that is the number of grams contained in 1 mole. The molar mass is always the grams contained in 1 mole of a substance. So these here are going to cancel out. We then calculate that answer. We take the 13.3, multiply it by the 68.95. Rounding it off to 3 significant figures, we wind up with an answer of 917. Any questions on this one here? All right, question number 2 on the Socrative app today was, have you heard of the D2L Pulse app for your smartphone or tablet device? I'm curious about this because I just learned about this one in the fall. So there's a number of you that haven't heard of it. Those that do use it, what does it do? Who uses it? Raise your hand. What do you use it for?
It tells us when the assignments are due and like when, and it tells you your scores.
Yeah, it tells you your scores. It tells you when assignments are due. Some people seem to have trouble figuring out that there's assignments due. They don't know. And I've placed all of that stuff into the calendar there. It does show up for my class, right? Yeah. So if you don't know what's due when, I'm giving you permission right now. Download the D2L Pulse app. Get it on your phone. Get it on your smartphone device. Sign up for notifications because it's going to tell you, not just for this class, but any of your faculty members, any of your professors that have placed those things into the calendar. It'll show up as prompts, and there should never, ever be any question as to what's due when, at least in this class. I can't speak for my other colleagues that teach elsewhere, but in this class, I place everything in there, the due dates. You'll have everything on there. Okay, so any questions on that? All right. With that then, we are going to go on here to the study of stoichiometry. And in our study of stoichiometry, and by the way, I don't use that word a whole lot. I've just used it twice now. I'll probably use it a total of 5 times this semester. When we talk about stoichiometry, there's 3. We define it like this. It is a study of the mass relationships in chemical reactions. It's a study of the mass relationships in chemical reactions. It's actually mass and mole relationships in chemical reactions. So I just said mass, but it's really the mass and mole relationships. And that's why we practice this first problem here today, because when we deal with this area of study, we're going to do a whole lot of gram to mole and mole to gram conversions. We're going to be using the molar masses a whole lot. And what I've tried to get you to do, up to this point, it hasn't been apparent as to why I've done it, but it's going to become apparent starting here today. I've been trying to get you to always include the complete units in the conversions. I know it feels like a pain in the butt to write lithium nitrate down 3 different times and then write it down in the answer again, so 4 times. But when we start working with chemical reactions, we're dealing with all sorts of different substances. And if you're not writing down the formulas each time, if you're writing down incomplete units, once you start getting different substances in the same calculation, you're going to get them all mixed up, and chances are you're going to make a lot more mistakes. So you should always get in the habit here when we work in stoichiometry, there's 4 times, to make sure that you're always using complete units when you're working with these. So to kind of use it as a preface here, I am writing out this equation as kind of a model of a chemical equation. This isn't a chemical equation. This would be like if we're making cars. If we want to make a car, let's say we're working at an automobile factory, and our objective is to make cars. And if we're making cars, each car needs a frame. We'll say that the bumpers are the same on the front and back, and you need 4 wheels. Together, 1 frame plus 2 bumpers plus 4 wheels makes 1 car. So the question is this, don't yell it out here because I think I put this on the Socrative app. How many cars can we make from this many frames, bumpers, and wheels? There it is. And feel free to ask your neighbor to see what they think. We had this many frames, bumpers, and wheels. How many cars could we make? Okay, I'll give you about 15 seconds to lock in an answer. Let's get them locked in. See, we still have a few more people. We'll count down on this. 5, 4, 3, 2, 1. Correct answer here is 25 cars. It is 25 cars. It's not 50, 40, and 25. We can only make 1 quantity of cars. It's how many cars can we make if we have these amounts. So we can make 25 cars. Now, how do we arrive at a 25? What do we look at to arrive at 25? Wheels. Why do we look at wheels and not frames? Right, because what happens once we get up to 25 cars? We run out of wheels, exactly. And if we run out of wheels, we can't make any more cars. Okay, so now we're going to have names for all of this stuff. And in fact, what I'm going to do here is I'm going to show you how to do this using dimensional analysis. Now, I know you probably did this in your head. You probably did 100 divided by 4. You probably did 80 divided by 2. You probably took 50 and divided by 1. Okay, but I'm going to show you dimensional analysis as kind of a way that we're going to do this when we work with chemicals. So using dimensional analysis, we would look at it something like this. We would say that if we have 50 frames, we'd like to know how many cars can we make. If we have 80 bumpers, we'd like to know how many cars could we make. And if we have 100 wheels, we'd like to know how many cars can we make. So what we're doing then, in essence, is that in the first one here, we're comparing frames to cars. And we look at these numbers out in front. And what do we call these numbers out in front? Coefficients. we look at those coefficients, and when we look at chemical reactions, we're going to wind up calling these coefficients molar ratios. Okay, now we could call them molar ratios here. Just understand if we have a mole of cars, that'd be a whole lot of cars. Again, we could say that 1 mole of frames would combine with 2 moles of bumpers to form 4 moles of wheels, or plus 4 moles of wheels, and would make 1 mole of cars. So we can treat those coefficients as if they stand for moles. And we would then say that the ratio between them is referred to as a molar ratio. And so, according to this equation, we have 1 frame for every 1 car. And when we have this relationship, frames winds up canceling out. And of course that's going to give us 50 cars. If we look at the second setup here, and we want to set this up, on the bottom we would put how many bumpers? 2 bumpers. And on the top we'd put in 1 car. And that's because as you look at these coefficients, we'd see that the ratio here is 2 to 1. So again, the units wind up canceling out. And if we calculate this out, we wind up with 40 cars. If we do the next one, we look at the coefficients. And we look at the coefficients on the bottom, we'd put in 4 wheels. On the top, we'd put in 1 car. We put these in because, again, if we look at these coefficients, the ratio here is 4 to 1. So there's 4 wheels for every 1 car. And so what we're doing really is we're using this molar ratio as a conversion factor. If we multiply this out, we wind up with an answer of 25 cars. Now again, with this batch of parts, we can't wind up with all 3 of these answers. We can only wind up with 1 answer. Again, the reason we wind up with 25 is because once we get up to 25, what happens? We run out of wheels, exactly. So, for these then, even though we calculated them, they cannot be the answer. This here can be the only answer because once again, once we get up to 25 cars, we run out of wheels. Now, to use some terminology that we are going to be using with the chemistry of this when we do this, is we say that the wheels are the limiting reactant. The wheels are the limiting reactant. And we define the limiting reactant like this. We define the limiting reactant as being the reactant that limits the amount of product we can make. The limiting reactant is the reactant that limits the amount of product we can make. In this case, the 100 wheels limited us to making only 25 cars. Over here, we say that these here are the excess reactants. And after we've gone, if this was in a factory, what does it mean if they are excess? After we've made all the cars, what's going to be true? There's going to be leftovers of these, exactly. These are going to be the leftovers. There's going to be some extra stuff of these at the very end. So we apply that to, and how much of the limiting reactant should be left at the end? None. The limiting reactant gets entirely consumed in a chemical reaction. And the excess reactants are the things that are left over at the end. This value out here we refer to as the theoretical yield. And the theoretical yield is the maximum amount of product that can be made. The theoretical yield is the maximum amount of product that can be made when all of the limiting reactant is turned into product. So again, the theoretical yield is the maximum amount of product that can be made when all of the limiting reactant is converted into product. One more time. It's the maximum amount of product that can be made when all of the limiting reactant is converted into product. So that should make sense. The maximum number of cars we can make in this case again is 25. 25 cars is the maximum number of cars we can make with these raw materials. And so again, this is a real world type problem. If you were baking cookies, for example, I don't know if anybody even bakes anymore, but if you did, and you started with flour and chocolate chips and sugar and eggs and whatever else to make your cookies. See, I've made cookies before. If you were to do that, again, when you start mixing them together, chances are you're probably going to have some, well, not when I make chips, but very often you're going to have some chocolate chips left over. You're going to have some extra flour left over. Actually, in my case, the limiting reactant is the chocolate chips. I like mine very chocolatey, and so I have a whole lot of excess flour and sugar when I make mine. Okay, so again, when you look at a process, the limiting reactant is the one that gets entirely consumed. It's the one that produces or yields the most product that we can make. And the excess reactants are the things that are left over at the end. So any questions with this? Okay, here's the next question. Following up on this previous problem, where we're showing the process again, if 23 cars were made from 50 frames, 80 bumpers, and 100 wheels, what is the percentage yield of cars? Now, I realize I haven't told you how to do this yet. This is a common sense one. If you know how to do percentages, percentages are the same no matter how you do it. So if you're not sure, talk to neighbor, calculate an answer, and enter it in. Okay, let's get your answers locked in. We'll give you about 10 more seconds. And we'll count down on this. 5, 4, 3, 2, 1. Correct answer here is a 92% yield. 92% yield. And that's because whenever you calculate a percentage, how are percentages always calculated? Part over the whole, then what? Times 100, exactly. So it's always the part over the whole times 100. So in this case, what is the part? 23 cars. What's the whole? 25. We then take this result, multiply by 100. We wind up with a 92% yield. Now if we're going to use some chemistry terms for this, instead of part over the whole times 100, here's how we use it with chemistry terms. We would say that the percent yield is equal to the actual yield divided by the theoretical yield, and then this result multiplied by 100. So now some other wording that we need to work with. Because sometimes it's the word problems that mix people up. So let's say that we mix things up a little bit here. And this is the way that you might see the wording for this problem. Again, we're going to the same process, the same factory process. We're making one car out of one frame, 2 bumpers, and 4 wheels. We'd like to know how many cars could be made using 100 wheels if there were an excess of frames and bumpers. And we'll give you about 15 seconds to lock in an answer here. We'll count down. 5, 4, 3, 2, 1. Correct answer here then should be 25 cars. Good, 25 cars. And so this is one of the ways that you will see some of these problems worded when you do your homework. And when we see them worded like this, what should we do to with regard to the frames and bumpers? Just ignore it, exactly. If you're given that there's an excess amount of a certain amount of reactants, they simply get ignored. They're not used at all in the calculation. The only thing that's relevant in this one is converting the wheels over to cars. Now going back to our last example here, what might some reasons be that we would wind up in this example with less than a 100% yield? Why might we only wind up with 23 cars?
Something could have broke.
Something could have broke, exactly. And that's true when you do anything. You break things. I try fixing things. I break them all the time. When you try making a sandwich, you might drop a piece of cheese or something on the floor, and the kitty's been there in the litter box or whatever, and it's got some kitty litter stuck to it, you know. You don't want to eat that, so you might just throw it in the garbage. That's going to reduce your yield of sandwiches that you're going to make, right? So same as if you're working in a factory, you might wind up, some wheels might be defective, you might wind up with less. The same is true in chemical reactions. When things react together, up to now we've assumed that whatever we see as a reactant and whatever we see as products are the only things that can be there at the end. The reality is that those are only ideal reactions. Very often we have some other side products that don't show up. We talk about the combustion of gasoline, or we talk about complete combustion as an example, assuming that everything's turned into carbon dioxide and water. But if there's incomplete combustion, we might also have some carbon monoxide that is present. And of course, if we produce some carbon monoxide, that is going to reduce the yield of carbon dioxide that's there. Okay? So when we've seen our chemical reactions, we've always assumed that they are 100% converted into whatever it is. The reality is that very often there's some other products that show up that we can't always account for. Now, what can the percentage yield never be? What value could we never find? What can't we have for our percentage yield? We can't have above 100%. And what else can't we have? Well, we could have 0. We can't have negative values, right. So we can't have less than 0. We can't have more than 100. So it has to be somewhere in the 0 to 100 range. If you wind up getting on an exam and you get an answer that's greater than 100%, what should you do? Redo it. Question yourself, because it's impossible to get a percentage yield greater than 100%. All right, let's go ahead and do some real problems involving chemistry. So let's do this one, and I'm going to see what you remember from our chemical equations. Let's write a chemical equation that shows the reaction between nitrogen and hydrogen to produce ammonia in the gaseous phase. And these are all gases, by the way. So let's write out a chemical equation that shows nitrogen reacting with hydrogen to produce ammonia. Not the ammonium ion, but ammonia in the gaseous phase. And once you write it out, then balance it. All right, compare your answers with neighbors. If you're unsure, you should absolutely be the one that's comparing. Okay? If you're not sure, you should be looking. Ask somebody that knows what they're doing. Okay, let's do this. Formula for nitrogen is N2. Formula for hydrogen is H2. And the formula for ammonia is NH3. Phase labels on all of these would be gas. Coefficients from left to right. What is the coefficient here? 1. Next one would be 3. Next would be 2. Wonderful. Okay, now, if we were to look at this equation, there's a number of different molar ratios we can wind up with. For example, if I'd asked what is the molar ratio between hydrogen and nitrogen, we would say 1 mole of nitrogen for every 3 moles of hydrogen. I got to remember here if I have any questions on this stuff for you guys. Okay. Now, one of the ways we represent it is we might put a colon between here, so this tells us what the molar ratio is. Another way we might do it is we would put in these 3 lines in here, which stands for is equivalent to. So according to this chemical equation, we'd say that 1 mole of N2 is equivalent to 3 moles of H2. And we didn't just pull these numbers 1 and 3 out of a hat. Where do they come from? They come from the coefficient. So the coefficient on nitrogen is a 1. The coefficient on the hydrogen here is a 3. Now, if we want to do another problem here, let's try this one. And now we're going to do this with respect to the amount of hydrogen and ammonia. So let's do this here. Let's figure out what is the mass of hydrogen, not the mass. Sorry, what is the number of moles? We're not in the mass yet. What is the number of moles of hydrogen required to make, and let's have something like 28 moles of NH3. So now if we're going to do this one, we start with what we're given. What we're given is 28 moles of NH3. What are we looking for? Moles of hydrogen, which would be moles of H2. Exactly. So now that we have this, we're going to place a conversion factor in here, and this conversion factor is going to be called a molar ratio. On the bottom, we'd put which units? Moles of NH3, and on the top, moles of hydrogen. And again, we picked these out. This isn't accidental. We picked these out because we want moles of NH3 to cancel out. We want moles of H2 in the answer. So what number are we going to put on the bottom?
2.
And on the top? 3. And where do these numbers 2 and 3 come from? They come from the coefficients in the balanced chemical equation. So the 3 comes from the H2, the 2 comes from the NH3. If we multiply this through, we'll take 28, multiply it by 3, and then divide it by 2, and we wind up with an answer of 42 moles of H2. Now, just as kind of a quick heads up here on this, what do we call this conversion right here? This again is called a molar ratio. And if we go back to where we started here today, what do we call this conversion right here? This here is a molar mass. This is a molar mass. So the molar mass is the number of grams contained in 1 mole. The molar ratio comes from the coefficients in the balanced chemical equation? Okay, you try this one, and I think I have this one up on the Socrative app, or it'll come up next. Oh, I forgot that one. I think I already gave you that answer. Let's try this one. We'd like to know how many moles of N2 will react with 9.33 moles of H2. Give the answer with the correct number of significant figures. Simply use MOL for the units in your answer. Again, we're using the same reaction. Give you about 1 more minute. If you're unsure, always compare an answer with the neighbor before locking in. Okay, we'll take about 15 more seconds. And we'll count down. 5, 4, 3, 2, 1. Correct answer here is 3.11 moles. 3.11 moles. Okay? So it looks like a few of us still missed this. Let's check the answer here real quick, how we do this. We start off once again with what we're given. In this case, what are we given? Of H2. What are we looking for? Moles of N2. So now we need a conversion in here. On the bottom, what are we going to put in? Moles of H2. On the top? Moles of N2. Right. So now we need some numbers that go in here. Where do these numbers come from? Balanced equation. So what number goes on top? 1. What number goes on the bottom? 3. Again, the 1 comes from here, the 3 comes from here. These come from the coefficients in the balanced chemical equation. We take 9.33 divided by 3, we wind up with 3.11. Okay, any questions on this one? What do we call this conversion here? Molar ratio. All right, so now, if you were to go into the lab, I know I'm not teaching you for lab this semester, but if you went into the lab, you're not going to be measuring out moles, you're going to be measuring out grams. Okay? So this is where we get into the real heart of what stoichiometry is. There's 5 times I've used it now. And that is, it takes us to where we really are going in the lab. And that is, you measure things in grams to start with. At the end, you're usually measuring your amounts in grams as well. And so we're going to look at a problem here. We're going to go and use the same chemical equation we have been using. So I'm going to rewrite it here. N2, gas. I don't know why that's doing that. I'm going to close this out and reopen it. Here we go. N2 gas reacts with H2 gas to yield ammonia in the gaseous phase. And then balancing it, we'll put in a 3 here and a 2 here. And here's the problem we're going to do on this one. We'd like to know what mass of NH3 could be made when 57.4 grams of H2 react with an excess of N2. So I'm talking about some of the problems that we've done thus far. If we see excess of N2, what does that mean we should do in this problem? Ignore it, exactly. This is just telling us we have plenty of N2 in here to react. We don't need to worry about this amount because there's more than enough here. So if you see that excess of N2, that basically means you could ignore that. But you're going to see it because we do need to know how much N2 is there. As long as you're told that there's an excess, then you're in good shape. So then we're going to look at what we're starting with. In this case, we're starting with how much? 57.4 grams. And again, it may seem cumbersome, but get in the habit of recording all your units. And the units are complete when you show the substance as well. And what are we looking for out here in the answer? Grams or moles? Grams of NH3. So we're looking for a mass, and mass again is measured in units of grams. So let's go ahead and do this one here. Now in order to bump up and use the chemical equation, we need to remember what these coefficients stand for. Now the coefficients could stand for molecules. We could say that 1 molecule of N2 reacts with 3 molecules of H2 to make 2 molecules of NH3. Or they could stand for moles. If we use the molar interpretation, where 1 mole of N2 reacts with 3 moles of H2 to make 2 moles of NH3. They do not stand for grams. So again, they could stand for molecules, they could stand for moles, they could stand for dozens of molecules, but it cannot stand for the mass. So that means if we're given grams, if we want to use this chemical equation, we have to use the chemical equation if we want to convert from one substance to another. What do we need to do to the number of grams here? Convert it to moles, exactly. So the first step, and this I learned one of my very first years of teaching here at No Grams. They had a high school teacher that said, when in doubt, convert to moles. If you don't ever know where to start a problem, convert to moles. So we're going to convert grams to moles. If we're going to convert grams to moles, what's going to go on the bottom? What units have to go down here? Grams of H2. What's going to have to go on the top? Moles of H2. Now we need some numbers in here. What number is going to go on top? 1's going to go on top. And what number is going to go on the bottom? Yeah, how do we find this number down below here? We need to go back to the atomic masses. So hydrogen here. One hydrogen has a mass of 1.008. So the formula here has 2 hydrogens in it. If you take 1.008 times 2, we wind up with 2.016. And the molar masses are always, this is always true, the number of grams contained in 1 mole, always. So at this point, grams of H2 are going to cancel out. If we go to the next step, we have moles of H2. We're trying to get over to NH3. How do we get from one substance to another substance? What conversion do we call it? A molar ratio. Molar ratio gets us from one substance to another. So if we want a molar ratio, what substance is going to go on the bottom? Moles of H2. What's going to go on the top? What are we trying to get to? NH3. So it shouldn't be a mystery. We're starting with H2. We're trying to get to NH3, so we want the relationship between NH3 and H2. Now what number are we going to put on the bottom here? What number is going to go in front of the H2? 3. What number is going to go in front of the NH3? And where do those numbers come from? The coefficients, exactly. The 3 is right here. The 2 is right here. So these come from the coefficients in the balanced chemical equation. And at this point then, what happens to the units? Moles of H2 cancel out. Well, now we have moles of NH3. We're trying to get over to grams of NH3. And how do we convert from moles to grams? What is that conversion we need to get us from moles to grams called? Molar mass. Exactly. And the molar mass is always the grams contained in 1 mole. And where's that mole going to go? On the bottom. Exactly. So we put 1 mole of NH3 on the bottom. On the top then we put the grams of NH3. And how do we figure out this number of grams? Atomic masses, exactly. We go back to the periodic table. We have 1 nitrogen. You'll need to put this in your calculators. 1 nitrogen. And how many hydrogens? 3. So we sum those together and we wind up with 17 point, what is it? 03? Okay, so 17.03 grams of NH3. And then what happens to units? NH3 is going to cancel out. So now everything's canceled out except for grams of NH3. This is set up to solve our problem. Remember that what we do is we multiply everything together that appears on the top. We divide by each of the values that appear on the bottom. So we'll take 57.4 divided by 2.016, multiply by 2 divided by 3, then multiply again by 17.03. If we do that, I get 323.25462963. How many significant figures should that answer have? 3. Rounding it off to 3, this answer is going to be 323 grams of NH3. Okay, 323 grams of NH3. Now as we look at these, let's ask ourselves again what these conversions are called. So we actually only introduced one new thing today. What do we call this conversion right here? Molar mass. And the molar mass is always the grams contained in 1 mole. What do we call this conversion right here? Molar ratio. And the molar ratio, where do these numbers come from again? Coefficients in the balanced chemical equation. And what do we call this conversion right here? This here is a molar mass. And the molar mass always is the number of grams contained in 1 mole. And I know I repeat myself here over and over again, but this is the thing you should be asking yourself then. The only new thing we learned today in this entire thing is the molar ratio. We've already learned about the molar mass. We just need to know where to use the molar ratio, and we use the molar ratio whenever we convert from one substance to another using the chemical equation. Let's try one more, and then we're going to practice to end the day. Let's do this. What mass of H2 will react with 3.25 grams of N2? What mass of H2 will react with 3.25 grams of N2? And again, we're using the same chemical equation. I'll write it here real quickly once again, just so it's in view. Okay, let's start off with what we're given. What are we given in this problem? 3.25 grams of N2. What are we looking for in this problem? Grams of H2. So we start off with the shell of what we're given, what we're looking for. First step is going to be take the grams of N2 and convert it to moles. So to convert it over to moles, on the bottom we'd put in grams of N2, on the top would put in 1 mole of N2. Then we need to calculate this number right here. And where's this number going to come from? Atomic masses. So we look at nitrogen. We have 2 at 14.01. That's going to give us 28.02. Grams of N2 cancel out. Next step, we want to convert N2 to H2. So to convert N2 to H2, what do we need? A molar ratio. So on the bottom we put in moles of N2. On the top, moles of H2. What number do we put on the bottom?
1.
And on the top? 3. These numbers come from the coefficients in the balanced chemical equation. It's a 3-to-1 molar ratio. Moles of N2 cancel out. And then we have one more step. We have moles of H2. We're trying to get over to grams of H2. So on the bottom here, we'd put in 1 mole of H2. On the top, we'd put in grams of H2. How do we get the grams of H2? Atomic masses. We come back here. The atomic mass of hydrogen is 1.008. We multiply that by 2. We do that, we wind up getting 2.016. And moles of H2 are going to cancel out. Well, once it's all set up, we go ahead and multiply this through. We take 3.25. Remember, we multiply together everything on the top. We divide by every value that's on the bottom. So 3.25 divided by 28.02. Multiply it by 3. Multiply again by 2.016. I get 0.7014989, etc. How many significant figures should this answer have? Rounding it off to 3, we get 0.701. All right. Now, just a very quick thing, and then I'm putting you to work. Let's review. What are the names of these conversions? First one here is called a molar mass. Next one is a molar ratio. The last one is a molar mass. The only thing new we learned today is molar ratio. All right, let's practice. And these are all going to show up in your Socrative app. I'm going to put them up on the board here as well. Open navigation. Am I going to do that? There we go. And the questions look like this right here. If you answer these 3 questions with 100% on the app today, you are free to leave. If you answer them with 100%, you are free to leave. But I do encourage you to help each other. What I will do is I will come back here and I will kind of scroll up and down so you can see where your percentage is at from time to time. All right? But please do help each other, and I will also walk around here and help you out if you need some help.